You are standing at the edge of a highway during rush hour. A truck weighing over 40 tons roars past you, tearing the air into invisible vortices that swirl around your body. That massive block of steel carries with it an entire ecosystem of classical mechanics kinetic energy. Torque, inertia, friction, all playing together in a symphony written by Isaac Newton centuries ago. And yet, at the very moment the truck thunders by, you notice something deeply unsettling. One of its components, weighing hundreds of kilograms, is floating completely off the ground. The very wheels designed to support tons of cargo are idle, hanging effortlessly, as if gravity were merely an optional setting. The sight feels like a bizarre graphics glitch in a physics simulation game. One part of the object refusing to obey the laws that the rest must still follow. But this is neither magic nor material rebellion. It is the outcome of an extraordinarily delicate negotiation between modern engineering and the immutable rules of nature. The lift axle, a component most people never notice, is not just an auxiliary add-on. It is a declaration that humans have not merely learned to coexist with physical laws. We have learned how to tune them, redistribute them, and in certain moments, reorganize their effects to suit our needs. To understand why these wheels can seemingly ignore gravity, we need to dive into 4 foundational pillars of physics: pressure, elastic deformation, rolling resistance, and lateral forces during turning. Each is a chapter in the story of how engineers found gaps between equations and turned those gaps into a transportation revolution. When a truck transfers its weight onto the road, it does not create a single downward force, but a distribution of pressure spread across every point of tire contact. Pressure, defined by the simple equation P equals F divided by A, translates a truth humans have long understood intuitively. The same force spread over a larger area becomes gentle, concentrated into a small area. It becomes destructive. A single nail can pierce skin, but a bed of thousands of nails pressed closely together becomes nearly harmless. The force never disappears. It is simply divided until no single point bears too much burden. The lift axle exists precisely to manipulate contact area at will. When the truck is fully loaded, the area through which force is transferred to the road must increase, preventing high-pressure zones that would damage the asphalt at a molecular level. Asphalt is not perfectly rigid. It is a semi-elastic polymer blend whose microstructure consists of tangled hydrocarbon chains, woven like a maze of fibers. When pressure exceeds a critical threshold,
visualizing physics concepts,
these chains slide past one another, creating permanent deformation. The ruts we see etched into road surfaces. Adding an axle under heavy load effectively expands the truck's footprint. It is the same logic a person uses when crossing thin ice. You lie flat to spread your weight, instead of standing upright and concentrating force in one spot. In heavy transport, dynamically controlling the footprint has become a refined engineering art, extending road life while protecting the vehicle from self-inflicted structural damage. But when the truck is empty or lightly loaded, a large footprint becomes a liability. The greater the contact area, the higher the rolling resistance, and the more energy is wasted. So engineers do the opposite. They pull the foot back, lifting the axle to reduce contact. If force were water, the lift axle would be a dam system, widening or narrowing the flow as needed. With what seems like a minor adjustment, the system completely reshapes how forces are distributed across the road, and in doing so, rewrites the behavior of the entire machine. All of this stems from a single equation. Point width, F(A), transformed from a static formula into a dynamic engineering tool far beyond anything a textbook can convey. To raise a steel axle weighing hundreds of kilograms, the truck does not rely on metal muscles. It uses something invisible, something we breathe every day: air. Air springs are proof that modern engineering can harness intangible quantities to perform tasks once thought possible only through brute force. Compressible air becomes a form of soft material capable of generating remarkable lifting power. At atmospheric pressure around 101 kilopascals, air seems weak, But confined and compressed, it can lift entire axles. According to Boyle's law, as volume decreases, pressure increases, transforming air into a compressible spring. This trapped gas not only raises the axle, but absorbs vibrations, dampens shocks, and most importantly, can be precisely controlled. It is this tunable elasticity that gives compressed air a flexibility steel simply cannot match. But the story does not end with air. Tires, often thought of as mere containers for air, are complex arenas of material physics. As a tire rolls, it undergoes constant deformation, flattening upon contact with the road, then rebounding as it rotates away. This process is not perfectly elastic. Rubber polymers exhibit hysteresis, a lag between deformation and recovery. Each cycle dissipates a fraction of energy as heat, a kind of unavoidable physics tax on motion. By lifting an unnecessary axle, the system avoids thousands of deformation recovery cycles every minute. This reduces
when
heat
the surface
buildup,
deforms, it creates
slows
a large
polymer
contact
aging,
area. This
and
dramatically
cuts
increases
total
the
energy
rolling
loss.
resistance.
In other words, the truck does not merely lift a wheel, it eliminates a significant amount of mechanical work required just to keep moving, repeated endlessly over thousands of kilometers. Switching between contact and suspension is not a whimsical gesture. It is a dynamic optimization rooted in elasticity and thermodynamics. What we see from the outside is a wheel vanishing from the road. At the molecular level, rubber chains breathe a sigh of relief, spared from countless unnecessary stretches. Among all the hidden forces acting on a moving vehicle, one is particularly quiet and persistent rolling resistance. It is weaker than air drag and less dramatic than centrifugal force. Yet it steadily drains energy. Unlike sliding friction, rolling resistance arises from deformation within the tire and road surface itself. Each flattened contact patch generates a resisting torque, converting motion into heat. More tires mean more contact patches and more energy loss.
The volume
Picture a person
decreases
dragging
and the
invisible
pressure
rubber
increases.
doors behind them.
This
Each
is
door slows
Boyle's
progress. Remove one, and the same energy carries you farther. The lift axle does exactly that. Reducing rolling resistance also lowers tire temperature. Heat accelerates microstructural breakdown in rubber polymers, destabilizing hydrocarbon chains and accelerating aging. This is why logistics companies treat rolling resistance as an economic variable, not just a physical one. A large portion of fleet operating costs comes from tire wear, caused by scrubbing and rolling losses, not mechanical failure. Driving unloaded with extra wheels on the ground is pure waste. Engineers call this loss of opportunity. Every kilometer traveled with a redundant axle down burns fuel without providing transport value. Across fleets of hundreds of trucks, covering hundreds of thousands of kilometers annually, these small losses accumulate into numbers large enough to justify redesigning entire transportation systems. The lift axle is not just about reducing drag. It prevents mechanical energy from leaking into places where it serves no purpose. If the truck were a living organism, the lift axle would act like an endocrine system, shutting down unnecessary organs to conserve resources for the journey ahead. Most people think wheels exist only to roll. But in multi-axle trucks, there are moments when wheels are dragged sideways instead. This phenomenon is called scrubbing, a highly destructive form of lateral friction. Scrubbing occurs because the turning geometry of multi-axle vehicles cannot satisfy every ideal path simultaneously. In tight turns, each wheel wants a different turning radius, but the rigid frame forces them into one path. The result, sideways sliding. This sideways force, called lateral force, does not slow the vehicle forward, but stretches materials laterally, a direction rubber polymers strongly resist. Molecular chains twist and strain away from their natural elastic orientation, creating invisible micro-damage. Over time, this leads to tearing and chunking patterns in tire wear. Lifting an axle alters the vehicle's geometry. The wheelbase shortens, transforming a cumbersome giant into a surprisingly agile structure. When load cannot be changed, geometry becomes the lever. Engineers understand this. Well, geometry defines behavior. And here, It determines how much lateral force reaches the tires during a turn. The system resembles how spiders retract legs when crossing narrow surfaces. The spider does not change its mass, it changes how many limbs engage the surface. Trucks do the same. Fewer axles on the ground mean fewer sources of unnecessary lateral force. Scrubbing also damages roads. Lateral forces tear at the asphalt surface, dislodging aggregate and weakening structural cohesion. By lifting an axle, trucks protect not only themselves, but also the infrastructure beneath them. Turning geometry, then, is far from a dry engineering concept. It is a living optimization between motion, material, and space, where every wheel angle carries a story written in force. True engineering intelligence does not lie in overpowering physical laws, but in adapting within their constraints. The lift axle, small compared to the entire machine, acts like a regulatory heartbeat, balancing pressure, optimizing friction, reducing energy loss, and reshaping motion geometry in real time. From afar, it looks like a pair of wheels floating above the ground. Up close, it is proof that humans understand physics deeply enough to negotiate with gravity, friction, and material deformation, turning immutable constants into advantages.
Significantly
No
improving
laws are broken.
maneuverability
Creativity
and
is
reducing
simply
tire
applied
scrub.
with precision. So, the next time those floating wheels glide past you on the highway, remember, what you are seeing is not a physical illusion. It is a victory of engineering thought over the rigidity of equations.